The Second World War witnessed destruction on an unprecedented scale. Bomber aircraft rained terror from above, forever changing the face of warfare. But in the skies above Germany, a new weapon was taking shape, something that would usher in the space age: the V-2 rocket. More than just a weapon, the V-2 was a marvel of engineering, a testament to human ingenuity and our endless drive to push the boundaries of what's possible. It was the first human-made object to reach space, paving the way for rockets that would eventually carry satellites, probes, and even humans beyond Earth's atmosphere. But the V-2's journey from the drawing board to the launch pad was fraught with challenges. Material shortages plagued the German war effort, and the rocket program was no exception. Engineers had to be incredibly resourceful, utilizing a combination of readily available materials and more exotic, harder-to-acquire substances. This is the story of those materials, the metals that formed the backbone of the V-2 rocket, and the challenges faced by those who sought to acquire them in a world at war. It's a story of innovation, ingenuity, and the lasting impact of a weapon that, while born of conflict, ultimately helped to propel humanity towards the stars. To understand the material challenges of the V-2 rocket, we must first understand its basic anatomy. This was no mere artillery shell lobbed across the battlefield. This was a towering behemoth of a machine. At its heart was the engine, a marvel of engineering that burned a volatile mixture of alcohol and liquid oxygen to generate thrust. Surrounding the engine were tanks containing these propellants, along with intricate plumbing and pumps to deliver them to the combustion chamber at incredible speed. The rocket's body was constructed from thin sheets of metal, formed into a streamlined shape designed to minimize drag as it hurtled through the atmosphere. And at its tip lay the payload, a 1-ton explosive warhead capable of leveling city blocks. Steel, the workhorse of industrial civilization, formed the backbone of the V-2 rocket. Its high tensile strength and relative abundance made it the ideal material for the rocket's structural components, from the massive thrust frame that supported the engine to the cylindrical body segments that housed the propellants. However, not just any steel would do. The extreme temperatures and pressures generated by the rocket engine demanded a steel alloy capable of withstanding immense stress without failing. Engineers turned to high-grade steels containing chromium and molybdenum, elements that added strength and heat resistance. These specialized alloys were not easily obtained, particularly as the war progressed and resources dwindled. The German steel industry, already stretched thin by the demands of the Wehrmacht, struggled to keep up with the rocket program's insatiable appetite for high-quality steel. While steel provided the V-2 with its structural integrity, aluminum offered something equally valuable: lightness. In the realm of rocketry, every kilogram counts. The lighter the rocket, the less fuel it needs to reach its target, and the greater its range. Aluminum alloys, prized for their high strength-to-weight ratio, were used extensively in the V-2's construction. The rocket's outer skin, fuel tanks, and even some engine components were all crafted from this lightweight metal. But aluminum production was a complex and energy-intensive process. Germany, lacking significant domestic sources of bauxite, the ore from which aluminum is extracted, had to rely on imports from occupied territories and allies like Hungary. Section 5. Exotic Fuels, the Power of Chemistry. The V-2 rocket was propelled by a potent mixture of liquid oxygen and alcohol, a far cry from the gunpowder that fueled earlier rockets. These exotic fuels, as they were known, offered significant advantages in terms of energy density and efficiency. Liquid oxygen, kept at a frigid -183 degrees Celsius, served as the oxidizer, while a mixture of 75% ethanol and 25% water acted as the fuel. The water helped to cool the combustion chamber, preventing the engine from melting under its own heat. Producing and handling these volatile substances presented a unique set of challenges. Liquid oxygen had to be manufactured on-site at specialized plants, while the alcohol fuel, though easier to produce, was still highly flammable and required careful handling. Section 6. Sourcing from a Reich at war. Acquiring the materials needed to build the V-2 rocket was a logistical nightmare. The German war machine, already stretched thin across multiple fronts, had to contend with Allied bombing raids, resource shortages, and a dwindling industrial base. Steel mills, aluminum factories, and chemical plants all became targets for Allied bombers, disrupting production and delaying the rocket program. The situation grew increasingly dire as the war progressed, forcing the Nazis to resort to desperate measures. Forced labor, often drawn from concentration camps, was used extensively in the V-2's production, a dark chapter in the rocket's history. The use of slave labor, while horrific, underscored the importance the Nazis placed on the V-2 program and their belief in its potential to turn the tide of the war. Section 7. The scientists behind the rocket. Behind the V-2 rocket stood a team of brilliant scientists and engineers, men who pushed the boundaries of technology in the service of the Third Reich. Chief among them was Wernher von Braun, a visionary engineer who dreamed of spaceflight long before it became a reality. Von Braun and his team at the Peenemünde Army Research Center worked tirelessly to overcome the technical challenges of rocketry, developing innovative solutions to problems of propulsion, guidance, and materials science. They were pioneers in their field, laying the groundwork for the space race that would follow the war. But the morality of their work remains a subject of debate. While some argue that von Braun was a brilliant but apolitical scientist simply pursuing his passion for rocketry, others condemn him for his complicity in the Nazi war machine. Section 8. A legacy forged in conflict. The V-2 rocket, for all its technological brilliance, ultimately failed to alter the course of the war. By the time it was deployed in significant numbers, the tide had already turned against Germany. But its impact on the post-war world was profound. Both the United States and the Soviet Union recognized the strategic importance of rocket technology, and they scrambled to acquire the V-2's secrets. Von Braun and many of his team surrendered to the Americans, while the Soviets captured key production facilities and technical documents. The V-2 became the template for the ballistic missiles and space launch vehicles that would come to define the Cold War. From the American Redstone and Atlas rockets to the Soviet R-7, the ancestor of the Soyuz rockets still in use today, the V-2's legacy can be seen in the design of rockets around the world. Section 9. Conclusion. The enduring impact. The story of the V-2 rocket is a complex and often troubling one. It is a story of remarkable technological achievement, driven by the ingenuity and determination of scientists and engineers operating under extraordinary circumstances. But it is also a story inextricably linked to the horrors of war, to forced labor, and to the destructive ambitions of a totalitarian regime. Yet, the V-2's impact on human history is undeniable. It marked a turning point in our relationship with space, paving the way for the satellites that connect us, the telescopes that reveal the secrets of the universe, and the rockets that carry humans beyond the confines of our planet. The V-2 serves as a reminder that even the most destructive of technologies can have unintended consequences, that our capacity for innovation can outstrip our wisdom in wielding it. It is a legacy we must grapple with as we continue to explore the cosmos, a reminder to use our technological prowess for the betterment of humanity, not its destruction.